Let's continue discussing the Erlangen program and properties of geometries. We started discussing the invariants. Do not confuse it with invariant sets. Invariant is a function defined for a given geometry that does not change under the group of transformations inherent in the given geometry. So we have some geometry of the underlying space S with group G, then function f defined on the figures of this geometry does not change, so function of some figure, I will call it f capital, will be the same after the transformation from group G is applied to the figures lying in the space S. So it will be T of F, where T belongs to the group G, the transformation of group G. So F is invariant, and its invariant, this is a function, usually can be expressed numerically if it does not change under the transformations from the group G. Example. The most interesting thing is an example. For example, in Euclidean geometry, complex plane and the group Euclidean transformation. There are invariants. A perimeter is the perimeter of a triangle or other figure. This doesn't change, of course, because the distances are not changed under the Euclidean transformations. Angle measures. The property of conformality. It's very easy to check this property. I am listing here because it's very easy to check these properties because they can be checked directly by applying the Euclidean transformations from the Euclidean group. We also know about this, of course, from elementary geometry, but we can prove it in our model of Euclidean geometry in the complex plane. Areas of figures. Just a few examples. Of course, all these invariants are inherent also in subgeometries. These invariants are also present in the subgeometries. Yes, if some function is an invariant in Euclidean geometry, of course it will be an invariant in subgeometries. For example, in the rotational and translational geometry, we can invent some other subgeometries. Translation geometries. You can invent some other geometries and maybe, and they will, if they are subgeometries of Euclidean geometry, they will have invariants. On the other hand, an example, a subgeometry may have an invariant that is not present in a greater geometry. Let's think about it. Can we produce some examples? May have an invariant that is not present in a greater geometry. For instance, in rotational geometry. In rotational geometry I can easily invent such an invariant. The sum of the distances from the vertices of a triangle to the origin. Indeed, if we have some triangle, suppose there is this triangle, we have the distances from the origin to the vertices of this triangle. This is the origin. So we have this distance, and this distance. Yeah? We have distance 1, distance 2, and distance 3. And we subject this triangle to a rotation. The distances would not change, right, under the rotation. The triangle will become another triangle, trying to make a realistic picture. Suppose something like this. And the sum of the distances will be still the same. So if I draw the distances, right, the distance will be, my picture is not very good. Just this new picture. This will come somewhere here. And this will come somewhere here. So these new distances, distance 1 prime, and distance 2, this will be distance 2 prime, and distance 3 prime, this distance, and this distance. Because we rotate, each vertex moves around the circle, the distances will be the same. Yeah? So d1 plus d2 plus d3 will be the same as d1 prime plus d2 prime plus d3 prime. And of course it follows from the simple fact, since d1 is equal d1 prime, d2 is equal d2 prime, and d3 equals d3 prime, And it's not an invariant in the Euclidean geometry, because in the Euclidean geometry we can just take this triangle and move it somewhere here, farther away from the origin, right? And for this triangle the distances will change. It is not an invariant in the Euclidean geometry. And you can provide an example in translational geometry as well. For instance, in translational geometry, in translational geometry, the slope of a line is an invariant. If you have a line with a certain slope, for instance this line, if this angle is theta, you know what is the slope? K is tangent theta, it's the slope. No matter where we translate this line, it will keep being parallel to the original line, and therefore this angle measure, or you can take as a numerical characteristic as the slope, will be the same. Whereas in Euclidean geometry, this line can be also rotated and the slope will change, of course. However, what's important for us to understand that if we have, I remind you again in a few more times maybe, that whatever is invariant in the greater geometry and invariant in some geometry as G is also an invariant in its subgeometry. And we will often use this property to prove result. It may be sometimes easier, we will see examples, to prove a result in a greater geometry, and then we will say therefore it holds in a subgeometry. We will use it pretty often. We will call this sometimes the proof in the spirit of Erlangen property. Now, what else? Let's see, more invariants. All these our invariants are based on the group of isometry so far in Euclidean geometry. What about a group involving similarities, for instance a homothetic group? A homothetic geometry. Homothetic geometry, yes? So it is geometry again in the extended complex plane, and the group H of homotheties. H, a group of homotheties. If I don't say about which point, so it will be about the origin, but the properties will be the same. Evidently, perimeters, areas are not invariants anymore, right? In contrast with the Euclidean geometry, because a homothetic may transform a triangle into a greater triangle, and the area of this triangle evidently is much smaller than the area of this triangle. The same story about the perimeters. However, some invariants of the Euclidean geometry still hold. Which invariants? You know which invariants? Conformality, is a property of homotheties. And I ask you to check it directly by a calculation. It's a trivial calculation, but it's a good idea to do it, just to reassert that you know what you can do and how you can do it. Check directly by a calculation. Conformality, what are there any other invariants? So therefore conformality holds, therefore the angle measure is an invariant in this geometry. And if you take a greater group instead of homotheties, we take similarities in general, so we combine homotheties, we may combine them with isometries. Still, angle measure is an invariant. What else? The thing called simple ratio. Simple ratio is an invariant. What is a simple ratio? Simple ratio is the following. Whenever you have a segment, suppose segment AB, and it is divided by point M into some ratio, yes? So AM over MB will be divided in the ratio 2 to 3. What will happen after a homothet? As a result of a homothet transformation, this segment will transform into segment A prime, M prime, B prime, and this ratio will hold A prime, M prime over M prime, B prime will be also 2 to 3, and you can also check it. You can prove it by means of elementary geometry from similarity of this triangle. Suppose this is O, the center of homothet, or some other point. You can prove it from the similarity of the triangles, or you can prove them by applying the homothet transformation. Yes, Tz equals Kz. That's a homothet transformation. You can check that the ratio of these distances will hold, and it is an interesting invariant. We will deal with it even more. This invariant holds even in a geometry much bigger that contains Euclidean geometry, and we will talk about it. What else we should talk about here? We may have a few different models for the same geometry. For instance, for the Euclidean geometry, we had, you can say it was abstract geometry when we discussed it axiomatically, or you can talk about the Cartesian model and the plane R2, or you can talk about the model that we have in the complex plane, where we modeled Euclidean geometry in a complex plane with the transformations. Yes? So for instance, for Euclidean geometry we may have a Cartesian R2 model when we have his coordinates x and y and the origin and so on, and the transformations that are Euclidean, we can transform vectors. Yes, we may have some vector and transform it into another vector. For instance, this vector v. We can apply Euclidean transformation. We can get new coordinates v1 prime, v2 prime equals Euclidean transformation of v1, v2, and it will be a certain matrix a1, b1, a2, b2 multiplied by v1, v2 plus a translation c1, c2. However, this transformation a1, b1, a2, b2 must be a so-called orthogonal matrix. Determinant of this matrix square is equal to 1. So it does not change areas, does not change distances. It preserves distances, preserves areas, preserves, you can say, dot product. It would be a good, easy way to say. And we can have the Euclidean geometry in complex plane, extended complex plane and Euclidean group, and model in the complex plane. Actually, you know that if you do not include without reflections, this matrix M will be just cos theta, negative sine theta, cos theta. It's a matrix of rotation. And we may have, so it's one model, and we may have another model in the complex plane where t of z will be e to the power I theta z plus b. Or you can, in order to keep notation consistent with this, here our translation vector was c, I would say plus, where c is a complex number, where c belongs to the complex plane. So these two models, this is just an example. What you can consider other models of other geometries. Two models of the same geometry must be isomorphic. What does it mean, isomorphic? There is a bijection between transformations in one model and in the other model. We can denote it symbolically. It will be more efficient than write a lot of words. So suppose we have some space S1, and in S1 we can take transformation T that belongs to group G. It's a group of transformations in S1 underlying space, right? And we will get again space S1 transformed, right? But we can also have another model. We will have space S2 and there is space S2. You can think of this as a complex plane complex plane, real Cartesian plane, real Cartesian plane. And there will be transformation tau, and tau belongs to the gamma group of transformations in space S2, and each of these transformation can be connected with each of transformation in S2 by means of some invertible transformation mu. Mu and mu minus 1 is a bijection. That, you know, this is necessary and sufficient condition for transformation to be invertible, because you want to be able to transform what we say in this model into language of model S1. So you can say that is a bijection or a lifting transformation for the isomorphism. Which isomorphism? S1G into geometry S2 gamma. Yeah, that's isomorphism mu, and it can be inverted, of course. What else we have to discuss? Sometimes we can use transformations in order to prove certain geometrical facts. So we will do it right now. We will consider quite a few examples. So these examples in your textbook are called proofs in the spirit of Erlangen program. What means in the spirit of Erlangen program? It means we will use transformations. So I will say proofs in the spirit of Erlangen program. So what are these proofs? There are a few different types of proofs. We will start with the easiest one. We will prove some known facts of Euclidean geometry using a group of transformation. Instead of proving a certain invariant in this geometry property in general, we will prove it in a particular case in which proof is easier, and then extended to the general case thanks to the transformations in the geometry. You can see. course, we have to talk in such cases only about the properties that are being invariant in the given geometry. Then we will have another type of proof. We will prove a certain statement in a greater geometry. And then we will say, oh, if it holds in a greater geometry, it must hold in a subgeometry. And by this, using this idea, we will prove rather difficult facts by very, very easy means. But first, let's consider this situation. So what is this situation about? Let's do the following. We will prove some statements of the Euclidean geometry. For instance, some property of a triangle. By locating this triangle in the complex plane in a convenient way, and then we say, since we can move this triangle around by means of Euclidean transformations, it will be true for any triangle which is not located necessarily in this position for which we prove a statement. That will be our method. The objection here may be the following. Oh, how can we prove the facts of elementary geometry if, in order to create this model, in order to create the model of the Euclidean geometry in the complex plane, we used facts of elementary geometry when dealing with complex numbers. That is true. However, the argument here is the following. Is it not a circular reasoning? No, the answer is the following. This geometry could be, we did not do it because it would be anti-natural, but we could theoretically, could be defined in the complex plane after we have defined the complex numbers axiomatically. Axiomatically as pairs of real numbers with certain operations. What would be this? We would say there are some pairs of real numbers. Z is always a pair x, y, and when we add z1 plus z2, we will add x1 plus x2, y1 plus y2. When we multiply them by real number, kz will be kx, ky. When we multiply two complex numbers between themselves, z1 multiplied by z2, or x1 y1 multiplied by x2 y2 equals x1 x2 minus y1 y2, and this one, it's the first part of the pair, real part, and x1 y2 plus y1 x2, and so on and so on. You see, it's a very unusual operation, multiplication, but we could have invented such an operation without appealing to any I squared equal to -1 or anything else of this kind. So that's the justification. We could have abstractly defined complex numbers, and develop the whole this model of Euclidean geometry as geometry invariant under transformations tz equals e to the power I theta z plus b, translations and rotations. So let's consider some examples of theorems in elementary geometry that we can prove. I encourage you to consider many other theorems. I will just select a few. One theorem is considered in your textbook and there is a misprint, so I will repeat it again. So, problem 1. Prove the midline of a triangle theorem. In particular, the segment that joins the midpoints of two sides of a triangle. The segment that joins the midpoints of two sides of a triangle is parallel to the third side and equals half of the third side. And actually this theorem in elementary geometry was was not a difficult one, but still it required some work to be done. So we have some triangle. In the complex plane, and I don't know what is triangle. Maybe okay, something like this. Triangle ABC, and we want to prove that if we connect the midpoints of these two sides, M and N, yes, if M and N are midpoints of the respective sides, then MN is parallel to AC and MN is 1/2 of AC. The length of MN is 1/2 of the length of AC. And instead of suffering, it would not be such a great suffering, but it would be a little bit. With this general triangle, I will do the following. I will move it in such a way that point B lies on the, it's not B anymore, right? It will be point, I will select the same notation as doing in your textbook. It will be point P. They have though a misprint in your textbook. And this will be point Q, and this will be point R, and this is point M goes into S, and this will be point T. All of this are complex numbers, yes? P, Q, R, S, T, all of them are numbers in the complex plane. So, how do I prove this statement? Very easy. I will say point S is a midpoint between P and Q. So S must be P plus Q over 2. T must be P plus R over 2, right? This segment is presented by the complex number S minus T. So S minus T equals, I will substitute P plus Q over T minus P plus R over T equals P over 2 and P over 2 will cancel each other. Will be Q over 2 minus R over 2. It will be Q minus R over 2. And therefore we can see that Q minus R is a real number. So S minus T will be a real number, so it will be parallel to the real axis. And the length of this number will be just 1/2 of the length of this number, yes? S minus T modulus will be 1/2 of the modulus Q minus R. That's it. This theorem has been proved. Because we can use the Euclidean transformations to move this triangle into any position, this theorem proved for triangle in this special position will hold for any triangle in the complex plane. So we will consider more examples in the next lecture.